Hey, so this is Joe, and this is the third video in Chapter 9 of Stewart's Calculus, and we're going to be talking about Euler's method. So Euler's method is a way of approximating certain points in the solution of a differential equation without actually solving or finding the general solution of that differential equation. So I'm going to write out what the formula basically says, and then I'm going to explain it a little bit, and then we're going to do some practice problems. So let's say we've got a differential equation, so we've got a derivative y prime is equal to some function of both x and y. So presumably this will be one that we can't, it can be one that we can separate, but the important thing to use Euler's method for is functions that we can't separate and find a general solution to, so thus we need an approximation sometimes for certain points in the solution. So we've got this differential equation. Let's say that we define step size to be some change in x, and that's going to remain constant throughout the approximation. And so based on this step size, we're going to have some x sub n is going to be equal to the previous x plus that step size. So we're going to be changing the x values that we plug into this approximation formula that we're going to get, and those x values are in increments of a constant step size that we define. So now the important thing about Euler's method is approximating values of y, values of the function itself. So the important part of the formula is we have yn, our new y, is going to be equal to the old y, yn minus 1. So the n minus 1, you can just think of that as old, the n, you can think of that as new, plus the step size. Now in your book it calls this change of x h. You can call it h if you want. I think change of x just makes a little bit more sense, times the derivative, so this function of x and y. And so this is how, and this is an approximation. And so that's the approximation right there. And so we can keep changing the step size to get to approximating y at a certain value of x. But what we need in order to use this approximation is we need some initial value of y. We need some initial condition, something that says y at x equals something is going to be equal to some number b. And so we need to have that initial information. We have to have one point of x and y as a solution for the differential equation at a certain point. And then we're able to use this approximation. So the best way to do a method like this, because it involves using multiple values of x and kind of iterating through this a couple times. So first thing, the smaller the step size, the more precise the approximation is going to end up being. But generally on the AP you're only going to need to do like 2 or 3 iterations with not a terribly outlandish step size. So let's try a sample problem of this. We're going to do problem number 24 on page 617 in your book. Alright, so this problem asks us to approximate, okay, so it gives us this differential equation. The derivative is equal to x plus y squared. We're given the step size 0.2, and we need to estimate y when x is 0.4, and we're given the initial condition that when x is 0, y is 0. So that's going to be our initial point. Alright, so that means our initial x is going to be 0, our step size is 0.2, y to the n minus 1, so our initial y is going to be 0, and so we add 0.2, or we'll find the derivative, sorry, this isn't y prime, that is, that's the new y, and then we're adding that to the initial y. So the new y, so I'm going to get rid of that column, sorry about that. So we've got the change in x, step size is 0.2. X to then, that's 0, plus 0. You can see where this is going. Our new y is going to be 0, but our new x is 0.2 because we add the change of x to the old x. So that's 0.2. So now the old x is 0.2, the step size is still 0.2, and the old y, the new old y, is 0. Now we're going to get our new y, and we have a step size of 0.2. Yeah, remember we were adding that to 0. We have a step size of 0.2. The old x is going to be 0.2 plus, and then the old y squared, but that's still 0, plus 0. So the new y is 0.2 times 0.2, which is 0.04. 0.04, and we add the step size, and so now we're going to be approximating for y when x is 0.4. So old x is 0.4, change of x still the same, it's 0.2. Now, and our new y is 0.04. So step size is 0.2. We've got a 0.4 plus 0.04 squared, and we are going to add that to the old y, which is 0.04, and this all works out to 0.0832. And then we add that to the 0.04, and we get, well, okay, so this is all 0.0832 right here, and then we add that to the 0.04, and this becomes 0.12032. And so that is our approximation of y when x is 0.4. So that's Euler's method. I hope that was helpful, and that wraps it up for Chapter 9. So stay tuned for Chapter 10. Thanks for watching.